Hi students, Professor Nugent here. In this video we are going to focus on the log-log population regression function. So in this case we have natural log of the dependent variable and natural log of the independent variable. Now we want to identify the interpretation of the OLS coefficient. So we subtract the original value of predicted y minus the new value of predicted y for a change in x, subtract the two, and we get this expression that the change in y over y is approximately equal to beta 1 times the change in x over x. Solving for beta 1 is approximately equal to change in y over y all over change in x over x for a small change in x. So this has a really cool interpretation when we have natural log on the left-hand side and on the right-hand side. So when we have natural log on the left-hand side and on the right-hand side, then we can interpret beta 1 as a percentage change in y given a 1% change in x. Okay? So in the log-log specification, beta 1 has the interpretation of the elasticity. Right? So given a 1% change in x, you get a beta 1% change in y. So this has a really cool interpretation when you have natural log on the left-hand side and on the right-hand side. Let's look at an example. When we take the natural log of test score versus natural log of income, first, you need to generate the new dependent variable and the new regressor. So you'll need to generate natural log of test score equals log of test score, same for income. And then the model is now a linear regression of natural log of test score against natural log of income. And we can estimate this using OLS. Predicted value of test score in this case is 6.336 plus 0.0554 times the natural log of income. So this tells us that a 1 percentage point increase in income is associated with a 0.0554 percentage point increase in test score. Right? So that's this coefficient. A 1 percentage point increase gives us a 0.0554 percentage point increase in test score. In other words, an income is up by a factor of 1.01, then test score is up by a factor of 1.000554. So this is really useful, and we have talked about different reasons to take the natural log of variables. One being to represent nonlinear relationships, two being to stabilize the variance of variables that have very large variance, and then three, we can see in this slide, that is to identify coefficients in terms of the elasticity. So if we wanted to know what the predicted change in test score was in percentage changes for a percentage change in income, then we would want to take the natural logs of these things. In this case, if we suppose that income increases from $10,000 to $11,000, that's a 10 percentage point increase, then test score increases by approximately 0.0554 times 10 percentage points, which gives us 0.554 percentage points. If test score were 650, this corresponds to an increase of 0.0554 times 650, 3.6 points, right? Because 0.554% is, in decimal form, 0.00554. An increase on top of 650 is 0.00554 times 650, 3.6 points. So the new test score at $11,000 is predicted to be 650 plus 3.6 gives us 653.6. And we can ask, how does this compare to the log linear model? So we have the log linear regression and the log regression plotted here. In the vertical axis, we have log of test score. And note that the log linear model does not seem to fit as well as the log regression. Let's put the log regression in beautiful rainbow colors. That log regression is much better at demonstrating the nonlinearity, the curvature that we see in the relationship between test score and district income. This is based on visual inspection, but it is a very powerful tool. Our eyes are powerful tools, and we want to plot these relationships, plot the relationships against the data, and see how well the predicted relationship matches the data. In summary, there are 3 cases differing in whether y or x is transformed by taking logarithms. The regression is linear in the new variables, and the coefficients can be estimated by ordinary least squares. The hypothesis test and confidence intervals are now implemented and interpreted as usual. The interpretation of beta 1 differs from case to case. The choice of specification, so the functional form, should be guided by your judgment. Which interpretation makes the most sense in your application? You will also run tests plotting the predicted values against the data. You can compare the r squared, but only in the case that the r squared, the adjusted r squared, only in the case that the left hand side variable is the same. So only in the case that it's either you're comparing 2 regressions where the left hand side variable is log of test score, or where the left hand side variable is test score untransformed, because then you're explaining the same variation. Alright folks, that is it for log transformations. In the next video, we will discuss other nonlinear functions and nonlinear least squares.